Welcome to our introductory discussion of acids and bases. In this video, we will describe the distinctive properties of acids and bases, define an Arrhenius acid and base, define a Brønsted-Lowry acid or base, and identify conjugate acid-base pairs and amphoteric species. Before we dive in too deeply into this topic, let's take a look at some of the common properties of acids and bases. When dissolved in water, acids are going to create a solution that tastes sour, conducts electricity because it frees ions. It's going to change litmus paper red, which we'll talk about a little later on. If it's not in a solution with water, it's usually going to be a liquid or a gas. Acids can be caustic, meaning that they can cause burns on skin or even dissolve matter, and they're all going to react with metals. On the other hand, when bases are dissolved in water, they create a solution that tastes bitter, also conducts electricity because of the formation of ions, changes litmus paper blue, is slippery to the touch, and does not react with metals. If they're not dissolved in water as a solution, they're usually going to be a liquid or a solid. For this unit, there are some acids and bases that you are going to need to memorize. You're going to need to memorize your strong acids and your strong bases, along with a couple common weak acids and weak bases. One way to help you easily memorize your strong bases is that if you notice, they are all of the group 1 metals plus calcium, strontium, and barium from group 2 paired with this OH or this hydroxide group. So rather than memorizing them individually, all you really need to know is that strong bases are when you have an OH or a hydroxide group paired with a group 1 metal or calcium, strontium, or barium from group 2. So what is the difference between a strong and a weak acid anyway? Well, ions are produced when an acid or a base dissociates in an aqueous solution. The greater the dissociation, the more ions are going to be present in the aqueous solution. Strong acids and strong bases dissociate nearly 100% into ions, whereas weak acids and weak bases dissociate very little into ions. The fact that strong acids and bases dissociate completely is particularly useful when we're working with concentration. So if I have one molecule of hydrochloric acid, when it dissociates, I get one hydrogen ion and one chlorine ion. If I were to have two molecules of hydrochloric acid, I would get two hydrogen ions and two chlorine ions. But since we don't often work with just one or two molecules, we work in much larger quantities in our moles, this ratio can also be scaled up. So for example, if I have 1 mole of hydrochloric acid, when that dissociates completely, I'm going to have 1 mole of hydrogen ions and 1 mole of chlorine ions. If I were to have 2 moles of hydrochloric acid, then I know after dissociation I would have 2 moles of hydrogen ions and 2 moles of chlorine ions. So take a look at this example. So we have potassium hydroxide, a strong base, and it disassociates into potassium and hydroxide ions. Well, if I have 3.5 moles of my KOH, my potassium hydroxide, how many moles of potassium ions and hydroxide ions am I going to be left with after the complete dissociation of my potassium hydroxide? Pause the video, take a moment to think about it, and then hit play when you're ready to check your answer. That's correct. If we have 3.5 moles of potassium hydroxide, because it's a strong base and dissociates completely, after dissociation we're going to have 3.5 moles of potassium ions and 3.5 moles of hydroxide ions. So what exactly is an acid and a base outside of the characteristics we've already discussed? Well, we're actually going to look at two definitions for acids and bases. The first of which is called the Arrhenius acid-base definition. According to Arrhenius, acids contain hydrogen ions and release them when they ionize, while bases contain hydroxide ions and release those hydroxide ions when they ionize. This means that an acidic solution is going to contain more hydrogen ions than hydroxide ions, and a basic solution is going to contain more hydroxide ions than hydrogen ions. So the Arrhenius definition is a good start, but it's not perfect and it actually doesn't work for some acids and bases. In fact, one base that we've already looked at that it doesn't work for is NH3 or ammonia, because NH3 doesn't have a hydroxide group, which the Arrhenius definition does require it to have. So for the most part for this unit, we're going to use the Brønsted-Lowry acid-base definition. So according to the Brønsted-Lowry definition, an acid is a proton or a hydrogen ion donor, while a base is a proton or a hydrogen ion acceptor. So what does that mean? Well, let's take a look at this reaction up here again. Our NH3 on our reactant side becomes NH4 on our product side by accepting a proton or a hydrogen ion to go from NH3 to NH4. And since our NH3 accepted a proton, that makes it a Brønsted-Lowry base. Our water, on the other hand, went from H2O to OH by donating a proton or a hydrogen ion. So that makes water our Brønsted-Lowry acid. Do note, however, that the acid, our proton donor, is giving that proton to the base. So in this case, our proton, our hydrogen ion, is going from our water to our NH3, from our proton donor to our proton acceptor. Let's take a look at one more example. So take a look at this reaction where you have HCl plus H2O gives you H3O or hydronium and a chlorine ion. Take a moment and see if you can figure out which one is the Brønsted-Lowry acid and which one is acting as the Brønsted-Lowry base. Pause the video, and then when you are ready, hit play to check your answer. So you should have gotten HCl as your acid, and you might have gotten it as your acid because you recognized that it was hydrochloric acid, and in this case, water is your base. But HCl is our acid because it is donating a hydrogen or a hydrogen ion or a proton as it goes from HCl to become Cl minus. It's donating that hydrogen ion or that proton to water as water becomes H3O by accepting that proton from our hydrochloric acid. So our hydrochloric acid is our proton donor, while H2O is our proton acceptor. So in addition to being able to identify our acids and bases, we also need to identify something called a conjugate acid and a conjugate base. So the first step in identifying a conjugate acid and a conjugate base is to identify the acid and the base. Your acid and bases are always going to be on the reactant side of your equation, and your conjugate acids and bases are always going to be on the product side of your equation. So for this reaction, take a moment and identify your acids and your bases, your proton donors and your proton acceptors. So hopefully you worked out CH3COOH or acetic acid to be your Brønsted-Lowry acid and water to be your base. Well, by definition, a conjugate acid is a substance formed when a base gains a hydrogen ion, and a conjugate base is a substance formed after an acid loses a hydrogen ion. So we can think of a conjugate acid as the substance the base becomes, and we can think of the conjugate base as the substance the acid becomes. So in this case, since our water becomes H3O, our H3O or our hydronium would be our conjugate acid. And since our acetic acid becomes CH3COO, this would be our conjugate base. These are also called conjugate acids and conjugate bases because it's what they act like when you go in the reverse reaction. So H3O hydronium is a conjugate acid because when we go in the reverse reaction, it goes from H3O to H2O, and it is a proton donor, so it acts like an acid. Same over here, CH3COO, our conjugate base, in the reverse reaction, it's going to be a proton acceptor and act like a base. So let's take a look at one more example to practice identifying our acids and bases along with our conjugate acids and conjugate bases. So try this example on your own, pause the video, and when you're ready, hit play to reveal the answer. So in this reaction, our NO2 is our base because it becomes HNO2, making it a proton acceptor and a base. And water is our acid because it goes from H2O to OH, so it's a proton donor. And because NO2 becomes HNO2, our HNO2 is our conjugate acid. And since our acid, our H2O, becomes OH, our hydroxide is our conjugate base. There's one other thing I hope you noticed about this reaction. In our previous example with acetic acid and water, our water acted as the Brønsted-Lowry base, where here in this reaction it's acting as a Brønsted-Lowry acid. That's because water is an amphoteric species, and amphoteric species are substances that can act as either an acid or a base. Water is one of the most common amphoteric species we'll see and work with, but there are plenty of others that can either be an acid or a base, depending on whether they are accepting or donating protons. This concludes our introductory discussion of acids and bases. Bring your notes and any questions you have with you to class.